Hi, this is Alex's World of Math, and today we're going to go through a method called stars and bars. So from the previous videos, we went through these three kinds um, of counting. So we counted how many ways to select k from a set of n elements, which are all distinct, um, where we have order sequence and repetition allowed, distinct choices, and also unordered with distinct choices. And remember that this choose formula was obtained by dividing by k. Um, and so our question is, what is this question mark? Well, I mean, divided by k factorial. Well, we can't really just divide by k factorial for n to the power of k. Why? You have n to the power of k over k factorial. If you're saying that this is the formula for selecting an unordered sequence with repetition allowed, then that means it should work for any integer, right? But what if we put k as 3 and n as like 5? Then 5 to the power of 3 over 3 factorial is equal to 125 over 6. But this is 20 and 5, 6. That's not integer. So it cannot be this formula. We just proved it false by a counterexample. So then what is, well, all right, let's start by thinking um, with an example, right? You're baking cookies and have 6 tablespoons of sugar. You want to distribute the sugar among 4 bowls, different bowls with various ingredients. The bowls can hold different amounts of sugar, including 0 tablespoons. How many ways can you distribute the sugar amounts among the bowls? Um, so notice that this is a unordered sequence. You have um, you have like groupings, right? You want to distribute this into 4 different bowls. These are different groupings. And so uh, you basically want to find uh, how many how many uh, how many ways to do so with also repetition allowed. Why? Because uh, you have each bowl that can be 0 tablespoons all the way up to 6 tablespoons. So they have different options. However, uh, However, the order doesn't matter. You just want to split them into the 4 different bowls. Um, and each bowl can have different amount of sugar, but each of them affect the outcome of the other. So we can't just multiply every single one. We can't just multiply 6 times 6 times 6 times 6. So how do we even think about this? Well, um, one way to do this is um but sorry, that example we'll explain that later. I think it's better if we use the general k and n for now. And then after we obtain our sequence, we can test it on that example. All right. So we can one way to think about this is all right. So first off, uh we have k elements, right? We're gonna choose k elements. So since it's unordered, we can express that as a set, right? And sets are all unordered. So so we have a uh set of like set of elements like A1, A2, A 3, comma dot dot dot, comma AK. And we chose from this set, right? So this is a subset of k elements from that set. These A's are not explicitly defined, but can be they're arbitrary. They can be any. They can take on any value of this after being chosen from this set. Um, so one way to think about this is, what if each of these elements had oh, I'm sorry. Uh, repetition is allowed. So these are not distinct choices. So this will not be a set. But if repetition is allowed, let's express this as choosing k slots, right? You have k slots. You have one. You have the first slot. You have the second slot. You have third slot. You have dot dot dot. Um, dot dot slots, and then you have up to k. All right, so you want to put this in k slots where repetition is allowed, but these are unordered sequences, so we need to still divide by however many arrangements. But we can't really. It's really hard to find the number of arrangements, like looking at each group, because the groupings all can be different numbers. They're not restricted by the distinct choices. And so one way to do this is for each element in this uh in this set, we can um represent them by multiplicities. So say like the number 2 here, it could appear at most k times, but it can also appear 0 times. If it appears 0 times, then then it like then it's not gonna be in this subset of, or like subgroup um of k elements. And so that means each element of that set, let's say the set 1, 2, dot dot, comma n. Let's label 1 as k1, 2 as k2, dot dot ki, n as kn. All right, so these represent the multiplicities of uh, each element in this set of 1 to n. And basically what happens, there's like, you can think of this as like, it's similar to the where we the binary set, right? Remember when we labeled each, or we gave each element in the original set either 0 or 1, and if it was assigned 0, it did not appear in the subset. And if it was assigned 1, then it would appear. In this case, we want to force this to have instead of an arbitrary amount of subset, like size subset, we need a subset of, or a subgroup in this case, because it's unordered, of size k. And so we're looking for size k, so that also means that each multiplicity, every single multiplicity added together is required to equal to k, right? We have k, yeah, you want you want a k size set. Uh, k size set. K size set. And in each of them, if the number 2 is picked 2 times, then it will have a multiplicity of 2, which means k2 will be equal to 2. And it goes the same for every single element. If they're picked x amount of times, then their multiplicity will be x. If they're picked 0 times, then the multiplicity will be 0. And so we're expressing this as ki's. So we have basically just k1 plus k2 plus dot 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 plus kn is equal to k, right? Um, plus kn is equal to k. And so if we have this formula, uh, this is very important because we can actually just use this formula and find the total amount of ways that we can like arrange this formula around. That will give us the total amount of ways we can form the groups with repetition, because this represents each group, right? Their multiplicities. And so if you understand that, then now we're ready to go to the next step. The k amount, each ki, the sum of ki of I is equal to 0, yeah, is equal to 0. Sorry, I is equal to 1 to n of ki is equal to k. And so if you add all this, then you're gonna get k, and you realize that each of these ki's are numbers and are integers, right? And k can only can range from 1 to n defined. So enters 1 to n. All right. And so after that, um, we can use this very uh, tricky trick uh, where we break the k down to k ones, right? Like k can be broken down into k ones. Just like 3 can be equal to 1 plus 1 plus 1. We're expressing k as 1 plus 1 plus 1 plus 1 k times. So let's rewrite this. K1 plus k2 plus dot 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 plus kn is equal to 1 plus 1 plus 1 plus dot 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 plus 1, where there are k times. All right. Um, and so now it becomes a little more apparent that we can think of this as trying to um, form groups represented by each multiplicity. Uh, K1 would be a multiplicity group, but if it like say if K1 was equal to 3, then that would be uh, taking these 3 added together. And another way of saying that uh, is also just um, saying that you want to combine the pluses together. Like which plus do you want to keep? So notice that there are k minus 1 plus signs on the right. But on the left-hand side, there are n minus 1 plus signs, right? So what we're trying to do here is we're trying to find how many times can these k minus 1 plus signs be ordered into or be distributed into n minus 1 groups, right? Uh, and why does this work? Because all right, you have the sum of ones, right? Um, say one group is the K2, K1, like if K2 was uh was a group, like each of these are groups, right? And if K2 is a group, then um it's gonna have its own like it's gonna have its own like domain. So it has like this, but there's in between these groups there's always going to be these pluses. And so we're basically trying to find which pluses are kept, right? Because there's gonna be some some of these pluses are gonna only n minus 1 of these pluses are going to be kept into these pluses because we're combining the ones to get these, right? Um, and so basically in each group you're gonna evaluate the plus sign. So if K1 was indeed you know multiplicity of 2, then these two will be combined together and you cross this out and say 2. But this plus sign is equal to this plus sign. So you're basically trying to order uh you're trying to find uh how many ways to get plus signs uh to become these plus signs. So you want to find how many ways to choose n minus 1 plus signs from the original k minus 1 plus signs from the sum of ones on the right side. Um, and you can think of these like just think of them as groups. You want to separate the plus signs into groups. You want separate like groups of one like certain ones and plus signs into groups. Um, but the plus signs next to the groups are going to be chosen as our indicator of where we are stopping. So say we chose this plus sign as this plus sign, then that means every single one in here are going to be evaluated. So this is going to be equal to K1 is equal to 3. So as long as we choose the plus signs, the groups will be chosen. And that's what's very important here, uh, that allows us to do this. And so how many ways are there to choose n minus 1 plus signs from k minus 1 plus signs? Well, that's just choosing, right? We're literally choosing groups. And so this gives us the amount of ways. Um, but there's something to note here. That's the equation that we got. Something very important to note here is that what we found was for k1 is greater than or equal to 1. Um, why is that so? Because we were looking at separating ones with plus signs. And so that means the plus signs can never go out of the ones. They can't. It was like you can't have a plus sign on the left of it because there was no other ones. Like if you look at the leftmost one in the sum of ones for the right hand side, there's only ones. There's only pluses between the ones. So that means there's no group that can be um, that can have a sum of 0. So what we value was for k1 is equal ki is equal to is greater or equal to 1. But what we want is k1 is greater or equal to 0 because we want the ki's to count for any multiplicity, including 0, 0 all the way up to n. And what we just did was for ki is greater or equal to 1. So how do we change from ki to ki is greater or equal to 1 to some ki is greater or equal to 0 instead? Well, um, it's pretty easy actually, because for each of these k1, k2, kn's, um, we're going to um, we're going to do something very special, and I'll go through that in the next video.